Okay, good afternoon, everyone. Welcome back to this webinar of the Energy Data and Modeling Program by the International Energy Agency. I hope you can hear me well. Otherwise, feel free to write in the chat if there is any specific technical problem, technical issue, so that we can try to solve it. So as you know, today we have as topic the modeling of the energy demand, and we will specifically focus on the building sector. So here, just a quick recap. You can see, like, as you know, you have been working with my colleague Zakia from the statistics team, and now we are dealing with the modeling sphere. So last week we had an introduction to modeling. Today, tomorrow, and the day after tomorrow, so this week will be pretty busy. We will work on the next three lectures on the modeling side. So today will be building sector, because we will use this sector to work and talk about the energy demand. Then we will have tomorrow the power sector, and the day after the hydrocarbon supply modeling. Then next week we will have not next week, but the week after. So starting from April 26th, we will have two sessions by two of our partners. First will be Polimi, Politecnico di Milano from Italy, an academic institution, and also again academic institution from the United Kingdom, the Imperial College. So before we start, again, same rules and, let's say, housekeeping rules, let's say. I invite you, if you have questions, to write in the chat section, or you can also directly write a question in the Q&A box, which is a functionality that Zoom gives us. Otherwise, I think it's also better, actually. If you prefer, you can raise your hand till using the, again, a functionality you should have as attendees for this webinar, and I will upgrade your status so that you can unmute yourself, also turn on your camera, and directly ask your question to me or to our colleagues, like one of our colleagues, which will join us later during the presentation, specifically for the Q&A session. So today's agenda, you will have, as I said, we will have a specific focus on the building sector. So we will start with like the activity, the structure and performance in modeling the building sector. You will have a specific part dedicated to understanding the drivers and how we can use those drivers in order to estimate useful energy, so the energy demand. And then we will have technology and fuel allocation. And finally, we will see how to estimate the final energy demand. And we will do a very, I wouldn't say very simple, but simplified version of an exercise through the Excel tool in order to estimate the final energy demand for a specific case study. So before going through the presentation, I would like to do a quick poll, as we used to do, through the menti.com website, which allows us to do a live poll. So you can start connecting to www.menti.com. I will share my screen, and I also will share the link for the presentation here in the chat so that it's easier for you to join. So just a second. Okay, so the link, I put it here in the chat so that you can directly use it. Otherwise, you can use also this code in order to enter the presentation. I give you just a few seconds. In the meantime, I start presenting you the first of the of the two questions we will have right now. So the first one is, in sub-Saharan Africa today, what do you think is the largest fuel used in the residential sector? So today, after traditional biomass. So you know that we have seen that and said that many times, that traditional biomass is the largest fuel used in the residential sector today. But my question here is, after which is the fuel which is currently at the second place? So you have electricity, you have oil, you have oh, sorry. Yeah, I'm sure. Yeah, okay. You have oil, you have gas, you have coal, you have modern use of biomass, and you have solar thermal. Okay, I leave you a few seconds. I see. Okay. Some of you are already answering. We have 5 answers. So I will move on. Like 2 of you got it right. The correct answer is electricity, which right now is at the second place after the traditional use of biomass in terms of fuel in the residential sector. And this is expected to be a very predominant fuel also in the future, since we are assisting, like we are seeing very sharp move to electrification in the final use of energy. And this is true in the entire world. This is particularly true and has been really true in, let's say, for example, in the European continent, where I come from, but it's also true in the sub-Saharan Africa region. So we'll move with the second question, which is, sorry, okay. The second question is now looking at the future. What do you think in the future will be the fuel that we expect to account for the majority of the final demand growth? So you have all the same fuels you had in the previous question, but now you are asked for each of them to select a value, like in terms of qualitative, let's say, qualitatively say, for each of these fuels, if you agree or not. So from not at all to very much, to if you agree that these fuels will account for the majority of final demand growth. Okay, so we have 3 people which answered. Okay, I see that we have electricity, we have modern use of biomass. I give you a few seconds more since I see that just 3 people answered. But in any case, with respect to this question, I won't give you, let's say, the answer. In any case, we don't have an answer. As you know, when we do modeling, we try to anticipate, but we don't know for sure if the results of our modeling exercises, let's say, are right, because we can't predict the future. But in the following slides, also through the help of my colleagues, we will see what are the results of our analysis, and what as the International Energy Agency we think when we are when every day we ask ourselves which fuel we expect to account for the majority of final demand growth in the next years and next decades. So I will go back to the presentation. Okay, so you should be able to see my screen right now. Sorry, I have an issue again with this. Okay. So coming back to the presentation, so I wanted to give you some insights from the IEA data collected, especially on the building sector. So here the question is, what does the future look like for buildings? So here you can see the energy demand and the CO2 emissions just from the buildings sector in the stated policies scenario. So if you remember, the stated policy scenario is that scenario that us at the IEA use in order to model the future, take into account as assumptions all the policies that all the countries around the world, as stated, they will, let's say, follow in the next years. So it's our, let's say, reference case scenario, because it's what the world, based on the commitment of each country, each government, each ministerial, of like all the officials in all the ministry, especially in the energy ministries, as committed to, let's say, achieve. So here, the first part, you can see, actually, we are not seeing yet the step scenario, because right now I cut this image, and you can see what has been the historical trend in terms of energy demand. So you see all the colors, and you can see how the energy demand in terms of source has evolved during the, like terms of fuels, has evolved during the last 2 decades. So you can see how, first, we can see how the total energy demand has increased from more or less 2,000 and a half mega TOE, so megatons of oil equivalent, from 2000 to 3,000 in 2020. You can see also how the specific energy demand from each specific fuel has evolved. So you can see that more or less we have coal, oil, and gas, which has remained more or less the same in terms of total amount, so in terms of mega TOE. But you can see how electricity has grown a lot. Also, that didn't change a lot, because you can see that more or less the area is almost the same. We have seen that also bioenergy didn't change a lot. And we can see, even if it's still not really relevant with respect to all the fuels, we can see how other renewables are also increasing a bit, especially in the last 10 years. I will try to use the pointer so that it's easier for me to, okay. So here you can see this dark green area, which is referring to the other renewables. Here on the top part, you can see on a secondary axis, which is in megatons of CO2. You can see the CO2 emissions. Again, just to underline, we are talking about just the building sectors, the building sector. You can see how also the emissions has grown according to the energy demand growth. So this is what we expect in the future, based on the stated policy scenario, which I already introduced you and also reminded you. So this is where the world could go. So we would expect, let's say, a smooth or linear growth in terms of total energy demand. And when we look at the mix, we can see that fossil fuels are not growing anymore. Like actually, we can see even a bit of reduction. Because we can see that coal is gradually phasing out. Oil is decreasing, but not at a very, let's say, high, decreased rate. And we can see how gas is replacing all these fossil fuel-based energy demand. On the other side, we can see how electricity is expected to grow a lot. And this is also answering one of the questions, like the second question I posed you through the Menti tool. And again, we can see how bioenergy is also decreasing a little bit. We have it, which is almost constant, and the other renewables, which are on the other side increasing. what you can see is that also we have the emissions in terms of megatons of CO2, which are not increasing anymore. We have little deflation, but we expect the total emission from the building sector to remain almost constant till 2050. This is clearly based, caused by this decreasing in the fossil fuel-based generation. Now we can see, because again, as I said, as I already introduced you also in the first lecture on modeling, we can see that there is also an alternative future, and one of these is what we try to depict with the Sustainable Development Scenario, which is a scenario in which we take into account a future in which all the countries in the world are able to achieve those goals, which are, for example, described very well by the SDG, so the Sustainable Development Goals from the Agenda 2030 from the United Nations. So here, again, if you remember this, till this point, we are talking about historical data, and from this value, like from let's say today till 2050, this is based on the results of our modeling exercises. So you can see that in this case, we have a very sharp decrease in terms of CO2 emissions. This is clearly in line with all the SDGs, but in particular, the SDG 13, which address the climate change issue. But on the other side, we can see, and also this CO2 emission is basically caused by this even, let's say, more like even deeper phase out of fossil fuel based generation. And you can see that, for example, coal is basically completely phased out. We have a strong decrease in the oil and also gas based energy demand. And we have electricity, which is completely, let's say, replacing all these decrease. On the other side, we can see that, again, it didn't change a lot, but we have bioenergy. Which is also decreasing, but the other renewables is also having a higher share in the energy, the total energy demand with respect to the other cases. On the big picture, you can see that compared to the stated policy scenario, also the total energy demand is decreasing, even though this scenario is taking into account also a growth in terms of social and economical parameters. And the reason behind, let's say, this decreasing in terms of energy demand from the building sector, even though we are taking into account a growth in terms of, for example, GDP and other economical parameters, is based on the fact that there is really a great increase in terms of energy efficiency, which allows, in this case, the world to let's say, to meet the energy needs of the people around the world, even though we use less energy, let's say, because we are able to do it with the higher efficiencies compared to what we have been able to do till today. So here I wanted to show you a bit of other analysis that we do in this specific case. We are talking about sub-Saharan Africa. Just a reminder, these graphs and also the next one I will be showing you come from the the Africa Energy Outlook. So that we did in 2019, and you can see that, for example, in this case, we are talking about the sub-Saharan Africa final energy consumption, and we can see that here on the left part, you can see fossil fuels. And on the right part, you can see the electricity. We have in both cases the information for 2018, which was the time in terms of data we had when we developed the Africa Energy Outlook in 2019, because we had the data till the previous year. And then you have in both cases the projection in the future. So what we expect will be the final consumption in both cases and in both scenarios. So here on both graphs, you have here the steps, which is the stated energy policy scenarios. And on the right part, you have the Africa case, which is a third scenario we developed here at the IEA, which is in line, I remind you, with the Agenda 2063, which is the strategic plan from the African Union, which, let's say, takes into account a brighter future for Africa. And as an overall, let's say, describe a future in which the GDP, for example, of the entire region is 60% higher, for example, with respect to what is in the stated policy scenario. So it's really a scenario which takes into account a great development in terms of social and economical parameters. So here you can see that the final energy consumption is increasing in both cases. So we have both in terms of fossil fuels and electricity, we can see the growth from 2018 to 2040, both in the STEP and in the Africa case. But we can see that the difference between the two cases, which refers to the same year, so 2040, there is really how can I say, a huge difference, because even though, as I told you, the Africa case has, let's say, higher growth in terms of social and economic parameters, and this growth, which clearly comes with higher final energy consumption, is represented by this purple box in both cases. But since we are also taking into account higher efficiencies, the expected final energy consumption is not at this level, the same, but we have a reduction with respect to what would be, let's say, achievable with, let's say, state of business as usual, let's say, efficiencies, but take into account the social and economical assumption of the Africa case. So we are able to achieve, let's say, a higher level in terms of socioeconomic benefits using less electricity because of the efficiency gains. So here we are talking about, let's say, a huge reduction in terms of final energy consumption. So I invite you really to really take into account energy efficiency, the energy efficiency aspect. So I will move to the Africa. Again, sorry, here there is an error. So I will skip this one and I will go back to that later on. So now I will move to the next, like the first part of today's agenda in terms of lecture. So we will start with these 3 points. So fundamentals of energy modeling, the activity of structure when working on modeling the building sector, and we will address really the topic of the drivers of the energy demand, especially, as I said, in the building sector. So just give me a few seconds in order for me to share the presentation. And if you have issues with sound or video, write it in the chat so that I can fix them.
important additional feedback needs to be considered: the impact that electricity and heat prices and fossil fuel prices have on end-use demand in general, and in this particular case, on the energy demand in the building sector. When working on the sector, the first step before doing any modeling is to analyze what do people want. What they want and use are called energy services. In the building sector, it can be space heating, cooling, lighting, cooking, etc. To meet service demand, we need energy, and this energy is consumed by different technologies. In the building sector, it can be air conditioners, light bulbs, radiators, etc. And for each equipment, we also have its associated efficiency. We therefore can distinguish three areas: activity, structure, and performance. The activity is linked to the energy services. The structure is linked to the type of equipment present in the building sector, and the performance is linked to the efficiencies of the different technologies. And all of this needs to be depicted in the model. If we look in more details at the structure of the building model, we see that we have different parts that make up the model. The first part includes all the inputs that are needed to do the modeling: historical data regarding energy balances, building stock, equipment sales, and also socioeconomic data like population, electrification rate, or GDP. And we also do some assumptions for the evolution of some of these data, so for instance, population. Some of these inputs will be used to compute energy service demand drivers, like household occupancy, floor area, or appliance ownership. Of course, these drivers will differ for each subsector. Indeed, the drivers are then used to determine the future useful energy demand, or the activity, as mentioned earlier. So for instance, for space heating, we can use the floor area as one of the drivers. In addition to that, we also need a number of historical and future technology data that describe the structure and performance of our system. These data include the efficiencies, the lifetime, the market share of the different technologies. We can then compute for each end use what technologies will meet the service demand, and we will finally estimate the energy demand by subsector and by fuel, as well as the investments and CO2 emissions. If we look in more details at the structure of a building model that make up the model. The first part includes all the inputs that are needed to do the modeling. As we've just seen, we need a lot of data inputs, as data are essential for energy models. Accurate balances are the basis for all modeling work, as we have seen and mentioned in the previous webinars on energy statistics. That's why it's important to build a data repository to organize all the data that you will use for your modeling. As mentioned, the data include energy balances, technologies data with efficiencies, costs, but also policy data that will impact the evolution of this sector. We will explore which are the most important ones in the next slides. As mentioned earlier, one important step of the modeling process is to define energy demand drivers, as they play a key role in describing energy consumption patterns in energy models. Thus, it's crucial to define the best proxy to describe past trends and possible future ones. Before looking in detail at drivers and different methodologies to estimate them, you can see here the general structure for modeling end-use sectors. So first, with the drivers and econometric analysis, we estimate the evolution of the energy service demand, or useful energy. Then, to meet the service demand, we allocate different technologies. And in the case of the world energy model, we use a cost-based approach to do this. Then, with the efficiencies of the different technologies, we can compute the final energy demand. If we go back to the drivers, we will look over the next slides at possible methodologies to identify the best proxy for each subsector. The projections of activity variables can be based on regression with respect to GDP or electrification, but we can also use different types of curves, like the S-curve. And as mentioned earlier, this requires to use different data that can come from the IMF or other national reports.
You've now been introduced to the importance of buildings energy demand modelling and the strong role of bottom-up modelling of energy demand for each end use within the building sector. And then following this, the processes and structure used in the modelling of buildings energy demand in the International Energy Agency. And now I'd like to focus in on one of the most important steps of our modelling process, and that is the definition of the best proxy to then describe the activity variable that can help us understand how service demand evolves for each type of building end use. So again, the proxy is the link that helps us to go from socioeconomic information to activity variables and then to services demand. Now, why do we need this link? Firstly, activity variables, we might have this information available for certain countries in the historical period, but we don't have it available for all countries over all of the time series, and we definitely don't have this information available for the projections. So therefore, it's up to us to take the information that we do have, and that is socio-economic information, and to use this information and these assumptions for the future to calculate our own activity variables. Once we've calculated these activity variables, we can use them in our projections to understand how service demand evolves, and then based on what technologies we choose, how energy demand evolves in our projections. Now, there are several types of activity variables that are of interest to us. Certainly in the building sector, one of the most important activity variables is household occupancy. So this is how many people live in each household on average. Now, household occupancy can help us to understand energy demand for end uses such as cooking or water heating, for example. Now, because we do not have information on household occupancy into the future, it's up to us to try and define a relationship between a variable that we do have information in the future and this household occupancy variable. So here we've chosen to plot values of household income against household occupancy. So we've taken all the data on household occupancy that we do have for historical periods for different countries, and we've put them on this chart against the GNI per capita, which is in itself an indicator of household income or of personal income. And what we can see is we have an inverse curve that's being drawn here. So that means that as we increase the average income per capita or per household, then we are decreasing the number of people per household. So here we're seeing a strong relationship between GNI per capita, so gross national income per capita, and a decreasing number of people per household. So we have on the right an inverse curve equation that can be used to define this relationship, and then can be very interesting for us and is a key step in our modeling to be able to say in the future, if from our external assumptions, which for us come from organizations such as the International Monetary Fund, the World Bank, and our own assessment and projections of economic growth and population. We then use these assumptions on economic variables to understand via this equation how household occupancy evolves in time. So that's just one example of this process of identifying a proxy that has a good relationship with the variable that interests us and using this proxy to describe the activity variable. So here, household occupancy. Now, another example of a relationship of interest to us in the building's energy demand modeling area is ownership variables. And so how does the ownership of a given appliance, such as a refrigerator in this example, evolve in time based on another variable? So here we've plotted ownership of refrigerators for all the countries for which we have data and over all the years for which we have data. And we've plotted that against here where we have a discriminant criterion, but we can very easily say that we can plot this against GNI per capita or even GDP per capita. So the most important variable to have on the x-axis is income in this case. And if we build this chart and fill out the data, we can very clearly see that there is an S-curve relationship between refrigeration ownership, so the average number of refrigerators per household, and the average income. And so that means that with time, as income increases, then we get to a point where the number of refrigerators on average per household starts to really increase. And then as we get to a point where households are increasingly rich, then the growth in refrigerator ownership slows down. Because once we get to a point where we already have at least one refrigerator on average per household, then obviously there's less need to increase and to continue to purchase additional refrigerators. So there is a saturation point, and that's why S-curves are so important, because they show us at the start that we might not have enough income even to think about buying a refrigerator, but at a certain point we start to cross that threshold and a refrigerator becomes a desirable and useful purchase and use of income. So we see that growth, that increase in the rate of growth of the S-curve, and then it flattens out as we start to saturate. So the S-curve is a very important indicator for understanding the relationship between many economic variables and the activity variables that interest us for buildings energy demand modeling. And I'll get to a description of the discriminant criterion and how we can draw upon several economic variables to influence and describe this curve in just a minute. But firstly, I would like to go through an example of air conditioning ownership. So here we've done the same thing as in the previous figure. We've plotted on the left-hand side, on the y-axis, the average ownership of air conditioners, and on the x-axis, the income, we have in our database, and we can see that it's a big cloud of points without a very strong relationship. So here it's difficult to imagine an S-curve describing the evolution of air conditioner ownership with income. But when we bring an additional piece of information to the picture, we start to see much clearer relationships. So now we start to plot data points, so air conditioner ownership and income, depending on the need for cooling in that region. So here the need for cooling is described in terms of annual cooling degree days. So a cooling degree day is a variable that can be calculated based on the threshold temperature in a given country and the average daily temperatures within that country. So here we can clearly see that for countries in darkest red, so the countries with the greatest cooling demand need, there is a relatively strong view of an S-curve that evolves in time. So we can see that as in those countries incomes start to increase, the rate of air conditioner ownership rapidly increases and moves towards 1, so an average of 1 air conditioner per household. However, if we look at countries in blue, so with very low cooling needs, then we can see that even when incomes, average per capita incomes increase to very high levels, the air conditioner ownership stays quite low. Because obviously these households, despite their high incomes, are prioritizing purchases in other needs because their cooling needs are not very high and not very pressing. So the message here is that sometimes we might have just the economic variable, so GDP per capita, and some information on ownership, but that's not enough to define a clear trend and a clear curve that can be useful for us. So sometimes we need to bring additional data to the table to help us understand the evolution and the relationship between the economic variable and the activity variable that interests us. Now, before going on, I'd just like to summarize some of the key end uses that we model in a bottom-up fashion in our buildings energy demand modeling, and the activity variables that we use to describe the energy service demand for that end use. And then further on, the proxy that we use, so the economic variable that is a key variable for us to help to understand the relationship between evolving economic conditions and the activity variable. And then finally on the right, the type of curve and the type of equation that we use to connect the proxy with the activity variable. So firstly, with cooking, the first curve that we saw was an inverse curve. And so for cooking, we use people per household to help us understand the evolution of service demand. So people per household is our activity variable. And as with all end uses in buildings, we're using GNI per capita, or you can use GDP per capita as well, as the most important proxy to help us describe the evolution of the activity variable. So we take our projection of GNI per capita that comes from other assumptions. So again, it might be World Bank, IMF. For population, it might be the United Nations. And then we use this variable via the curve, so the inverse curve in this case for cooking, to describe people per household and understand the evolution of people per household in time. Use an S-curve because the activity variable is floor space per household. Rich, so does the floor space of those households increase, and then we get to a point where there's saturation, and so the S-curve starts to flatten out. For water heating, it's again a question of describing energy service demand by the number of people that live in the household, because if we think that each person in the household may take 1 shower per day, therefore the energy demand need for water heating is dependent on the same as for cooking. But then if we look at air conditioning, so cooling and appliances, then it's a question of ownership. How many air conditioners or how many refrigerators, televisions are owned on average by the household? And then how does this ownership evolve based on increasing income? So again, an S-curve rapidly increasing at a certain point. Now, just a note here on cooling. We could also say that floor space per household is an important variable, because if we're trying to cool a much larger household with 1 air conditioner, then we're going to be having a higher energy service demand. So we can certainly look at both variables, firstly the ownership rate, and then also if we have an increasing number of meters squared per household, that will also increase the floor space, the energy service demand, sorry. So in cases like this, we can look at having 2 activity variables that now, to move on, I wanted to come back to the fact that sometimes we want to bring in additional variables. So if we look on the left-hand figure, the x-axis here is just GNI per capita. So it's an income proxy, essentially. So we're taking our income variable and we're using this to describe the number of units per household. But we can see that the curve is quite cramped. It's really not an easily defined S-curve. And that's because in the first, let's say, $5,000 of GNI per capita, and it's all happening very rapidly, and perhaps economic variables such as GNI per capita are not the perfect variable to understand what's happening in this first part of the curve. But now if we turn to the right-hand side figure, then we can we use here a discriminant criterion. So this is basically saying it's a It's a variable without a unit, which is just an indicator that combines several proxies. So it's combining GNI per capita, so it's taking the economic variable, but we're also bringing in information on the electrification rate within the country and the urbanization rate. Because when we start plotting this data, we clearly see that not only does the economic variable influence ownership, but so does electrification rate and urbanization. Because obviously we're not going to buy a refrigerator if we do not have access to electricity. So despite the fact that we might have an income, if without electricity, there's no point buying a refrigerator. So this is, it seems evident, but obviously becomes very important when we start translating it into these curves, and we can see this flat period at the beginning for those that still don't have access to electricity, despite the fact that they might have an income. And likewise, the data shows that with higher levels of urbanization, we also have higher levels of refrigerator ownership. And so we bring in these three different variables that describe and a geographical trend and bring that information together to build this discriminant criterion, which then helps us to get a much more clearly defined S-curve, which is then more useful in understanding in the future with a given a value for energy access, for income, and for urbanization, what might we expect in terms of ownership. So this is multivariate analysis and multivariate regression, as opposed to the earlier examples which were shown, which were using a single variable, so GDP per capita in those instances. Okay, now let's run through the principles of multivariate analysis for using many or several economic variables, population variables, or other interesting variables for which we have information to describe the evolution of activity variables. So the first point here is to look at the data that we do have. So taking the data we have on, say, if we're interested in refrigeration ownership, looking at the available data on refrigeration ownership, selecting a set of these data points which seem like a good, clean trend, and then trying to match these data points with available variable data on, say, GNI per capita, GNI per, or GNI absolute values, electrification rates, weather data perhaps, or any other variables that might be available. And then what we can do is plot all these variables together on a chart. And so, for instance, we'll have our variables on the y-axis on refrigeration ownership, and then we'll be plotting that on the x-axis against lots of different variables again and again to try and understand, is there a relationship between that variable refrigeration ownership and the variable that we're putting on the x-axis. And so what we can do, what we achieve by doing this, is we identify the most important variables that seem to have some sort of relationship between this variable and refrigeration ownership. And then we can partition the data into similarities, or based on what the data is actually describing. So for instance, if I take GDP per capita or GNI per capita, they're very similar data points. And so within this multivariate process, there's no point having data points that overlap and describe very similar trends. So even though both GNI per capita and GDP per capita are very useful variables that can both be used to describe the evolution of my activity variable, I'm not going to put them both into this multivariate analysis because they are describing the same things. However, if we look at a variable such as electricity access, then that is removed from GDP per capita and describing a different set of trends, and therefore we would put that in another class, and it would be very useful then to have variables from different classes, for instance 2 or 3 variables from 2 or 3 different classes, and bring these together to then feed into to establish the best combination of these descriptive variables that can be used to describe our activity variable. So once we have the 3 or the 2 variables that we've chosen, then we want to use a certain type of multivariate regression to understand what the best combination of these variables is to best describe this activity variable trend. So for us, we use canonical variate analysis. And so that's something that, that you can look up and try and understand the processes involved, or there's many other multivariate regression techniques that can be used to combine several variables to deliver one discriminant criteria, so one variable that combines all this information and then can be used for us to plot and understand the. That's then step 5. Once we have this relationship defined, then we can use our projections of, say, electricity access rates, of urbanization, of GDP per capita, feed all this information in, calculate our discriminant criteria, then take the discriminant criteria, put it into our curve equation, so our S-curve equation in this case, and then that will give us a forecast of the ownership of the activity variable. Now, the final point I want to make before I pass on again here is what we do with tracking data and how do we project the variables that interest us when we do not have the available historical data. So just take a step back. The first thing we do is we bring all the data that we do have together for all the countries that interest us. And then what we'll do, we'll divide the countries into different classes based on the type of, I guess, the category of the country. And so, for instance, we would bring countries together that have similar economic contexts, that have similar climatic and population growth contexts. So here on the left, we can see we've put countries, so country A, B, and C into different classes. And so we have several different classes for countries across the world. But for instance, if you're looking just at the African region, it might be pertinent just to have one class and to not bother about defining different classes. Now, once we've done that classification by class, then we need to look at the data availability for each country within each class. So for instance, if we take the example of country A, then country A is a country that is well informed in terms of data. So we have historical data available for many years for the activity variable that interests us. So it could be household occupancy, it could be refrigeration ownership rates, it could be floor area per average household. So here we have the information we need historically to be able to build the curve, build a robust equation that then can be used for the projections. However, for many countries, this unfortunately isn't the case. We do not have this data available. So for many countries, we find ourselves in the position of country B. So that means we're poorly informed. We might only have a couple of data points. So there might be a data point from a survey that's taken place only once, or maybe 5 years ago and 10 years before that. And so that means that we don't have sufficient data available to build a robust and reliable curve, so an S-curve equation, for example, and then to be able to use this S-curve equation to project activity variables into the future. And so what we do in this case is we use the curve that was described by all the countries for which we do have data. So we take the average curve of all the countries in class 3. So for instance, if we put all the data for ownership of refrigerators for countries in class 3 together in one figure, and then we use that to describe, to build an S-curve, and we have the equation for that S-curve, we can then use that S-curve equation for all countries that find themselves in the position of country B. But we shouldn't forget that for country B, we do have 1 or 2 data points. So what we'll do is we'll then shift the curve up or down to make sure that the curve is running through the most recent historical data point that we have available. So that's a way of ensuring that for us, we can use these curves to describe the trends for the 1 or 2 data points we do have, and to backfill the missing historical data, as well as understanding how these activity variables will evolve in the future. The final situation is the situation of country C. So this is a country for which we have no data at all for activity variables for the end use that interests us. So in this case, we have no other options all we can do is take the average curve of class 3. So the average, that means country C will just be described by the average throughout, because we don't have any data points to be able to shift and run through those data points. And so we go straight through to the projections of the activity variables using obviously the economic variables that are specific to country C, but using the S-curve or the inverse curve equation, that is the average of all the countries in class 3. So this is a very important point on how to find the data and then what to do with the data, and what to do, very importantly, when we don't have the data, all the data that we need to build these curves and therefore to produce. So obviously there's many different sources available for countries across the world, but in many African countries it can be quite difficult to find this sort of data. So at the International Energy Agency, we've often looked to surveys such as the surveys conducted by USAID, and we can find these surveys online, the DHS surveys, and often there is information within those surveys that can be used to help us in this modeling process. Alternatively, there can be specific literature on a specific country based on surveys conducted within that country, or based on academic work. But basically, the first step certainly is to look for the data that does exist for the end users that interest us most, and to contact or reach out to as many people as you can to try and get the best data and ensure that you start with the strongest foundation.
Okay, perfect. So let's go back to our presentation. I hope everything was clear and that you can see my screen. I wanted to go back to the presentation with respect to that slide I skipped earlier, in which I wanted to have, let's say, to look more specifically at the issue of cooking. So based on the data we have collected and we are working on, especially with the World Health Organization, we observe, let me just activate the pointer. Okay, we observe that today most people in sub-Saharan Africa are still relying on solar biomass under traditional use. So as you can see from the first pie on the left, so something which is definitely not considered as clean cooking. So under the stated policy scenario, first of all, I would like you to have a look also at the growth in population, because here through the pie chart, you can see the shares of the different technologies and fuels. But you have to take into account that here we are talking about more or less 1 million people in 2018, but in 2030 we expect more or less like 400 million people more in the sub-Saharan Africa, so reaching 1,400 million people, so more or less 1 billion and a half. So by the end of the decade, based on the stated policy scenario, the number of people would decrease, those people which rely on traditional solid biomass, and we would expect more people to be relying on LPG, on improved cookstoves, for example, as well as other clean technologies like, for example, electricity we have, and also biogas. So, but in any case, here you can see that we are talking about the 50% of 1,400 million people still relying on traditional use of biomass and also kerosene. So on the third pie is our Africa case for 2030, which is, let's say, a presentation of a brighter future, which we think is possible, is achievable. And in this scenario, one specific assumption is that everyone in the region has access to electricity, but especially also access to clean cooking equipments and fuels. So again, we have improved cookstoves, which now has an higher share of fuels and technologies for like used for cooking. we have also LPG, and we have also other clean technologies. So it's important to see how to bridge this gap and achieve, let's say, full access to clean cooking for all in this Africa case for 2030. LPG, so liquefied petroleum gas, is we think is the most scalable solution for especially urban settlements, because we know that urbanization is a phenomenon which exists right now, and we expect it to be really relevant in the future in all scenarios we are considering. So we think that improved biomass and LPG will be really helping achieving, like, bridging this gap. So with LPG more on the rural part, and improved biomass cookstoves in the rural areas. Okay, so I will move to a quick Q&A session. If you have questions, feel free to so write in the Q&A box or raise your hand so that I can give you the floor. I don't see any questions, so in the meantime, I will go back to the Menti online poll tool. But if you have questions, feel free to put them in the chat. I can answer them immediately, or otherwise we can also postpone them to the last part of the presentation, in which we will be joined by my colleague Victor. So again, in the chat, you should have you can find both the link to the menti.com online live poll. You also have the code. So I hope all of you are able to, again, go back to the presentation. We have two more questions to ask you. So in the meantime, I will introduce you to the first question. And as I see that some of you are answering, I can close it. So the first question is, if we have the energy consumption of an AC unit, which is, so AC stands for air conditioning unit, what is the most important parameter to estimate total demand? So we are asking you, you are a modeler, which, okay, perfect. I see there is already a question, an answer. So I hope everyone was able to connect to the menti.com website. So when you have to model the energy consumption for an AC unit, what is the most important parameter to estimate total demand? So is it the floor space, for example, of an household? So which is clearly measured in meters square. Square meters. You could use the number of households, or you could use the number of units per household. So let us know which is among these three parameter, the one you think is the most important when estimating the total demand for AC conditioning in terms of energy consumption. Okay, I see 4 people answered floor space, 2 people answered number of units per household. So I will show you, sorry, okay, okay. Sorry, okay. Okay, so in this case, the answer is floor space because sorry, my bad. That's another. The answer is number of units per household, because the more units you have in the household, the more the AC unit will play, like the AC unit will need energy, because clearly, yeah, I guess you can imagine that. But how can I say, all the other 2 parameters are really important, because it's not just knowing how many units a household has, but also how big those units are. So at that point, you would move to estimating and using the floor space parameter. But if we have to move from the single household to the entire, I don't know, a community, a city, a region, or the entire country, you have to take into account clearly the number of households in your target area, so that you can estimate the total energy demand and total energy consumption for the AC unit. And this question is really important because actually at the end of this lecture, we will be doing a small exercise. I hope some of you maybe already started doing it, because it's in our handbook and also in the online Drive repository. And we will be doing an exercise which is actually taking into account, trying to estimate the energy consumption of for the AC units for an entire country. So the next question is, if we have the energy consumption of a water heater of a household, what is the most important parameter to estimate total demand? So here you have floor space as for the previous question. So the space in square meters of the entire, for example, the entire household. You have the number of households, and you have also the household occupancy. So how many people there are, for example, on average for a country, an area, for each household. So the question is, if we have the energy consumption of a water heater of a household, what is the most important parameter to estimate total demand? So we have one person which answered household occupancy. In the meantime, if you have questions, especially also related to these questions I'm asking you through menti.com, feel free to write in the Q&A box in the chat. Yeah, the Q&A box is better. Also, you can raise your hand so that I can give you the floor and the possibility to unmute yourself and directly ask the question. So I see all of you basically answered the occupancy, the household occupancy, and this is the correct answer. But again, it really depends on the scale you are looking at, because if you are modeling just one household, clearly knowing how many people are living on average in one specific household, is the most important parameter to be taken into account, because it really depends on how many people there are, let's say on average, the needs in terms of energy consumption for water heaters. But again, if you have to scale, so to move from the single household to a city, a region, or the entire country, you have to know what is the total number, the total amount of households in your target area. Perfect. So this is done. So we will go back to to the presentation, and then we will have a session on the exercise and also the Q&A, the final Q&A session. So let me know if you see and hear well the video. Otherwise, I can fix any problem that may arise.
Once we have determined past and projected activity variables and service demand intensity, the total energy service demand, or useful energy, can be computed. I on end-use intensity, which is derived from our projections of activity drivers, as well as other data coming from our database, like the historic energy demand by fuel and end users, historic and projected temperatures. So we usually use heating degree days and cooling degree days, or historical technology market share and efficiency. For instance, with all this information, we can compute the energy intensity per square meter for space heating. Once obtained, the total projected service demand, we can now reflect on which technologies will meet the demand. So for each year of the projection, we can compute the total energy service demand that needs to be satisfied by new equipment by accounting for new incremental demand and considering the retirement of existing technologies. So of course, in later years of the projection, we also have to take into account the retirement of technologies that were added by our model. So how do we do this? For this, we need to have a detailed stock accounting. So with the historical market shares and efficiencies, we can compute the stock of existing technologies. And with the lifetime, we can determine the remaining stock for each year of our projection. And finally, we can compute the service demand to be met with new sales. So the sales of new equipment need therefore to replace previous equipment and to meet new demand for energy services. So you can see that the lifetime of equipment and its age distribution can play an important role in the capability of the system to renew the overall technology stock. In countries with burgeoning energy demand, such as in developing countries, the share of replacing old infrastructure and technologies is more limited, while its weight is more important in advanced economies. Now we have to determine which technologies will meet the service demand. The technology and fuel choice depends on a variety of elements, and first of all on the available technologies for each subsector in each market considered. That's why we have an important database sector. So for instance, you can look at the cooling subsector and you can see the different types of air conditioner that are in the model. The choice of technology depends on various parameters. The available potential of renewable resources can play a very important role, as well as several energy policies such as energy efficiency standards. In the World Energy Model, we rely mainly on a cost-based approach to determine which technologies will be installed. For this, we need to compute the cost associated to each technology, which includes the investment cost as well as the operation cost. For instance, for an air conditioner, we must take into account the price of this AC, but also the price of electricity that will be consumed by this technology. In our model, we assume that the technology share will be proportional to 1 divided by the specific cost of this technology. This least cost approach is often the most used criterion to select the technologies, but it's also important to consider boundaries to reflect market failures, behavioral patterns, and energy policies. For instance, we can set a minimum target for heat pump to be installed if we consider that energy policies are pushing the development. Here you have an example of the projections we made for various lighting technologies. On the left, you have the evolution of efficiencies, and on the right, the evolution of the market share of the LED. So with this information, we'll be able to compute the main outputs of the model. So you can see that estimates of historical efficiencies and performances of equipment and possible future evolutions are key parameters to make reliable estimates. That's why technology partnership, sharing information, and continuous interaction with the energy industry are really crucial elements to achieve it. As said before, once the technology choice is determined for each subsector for each projection year, together with the market share, efficiency, and fuel of use, the final energy demand can be computed, as well as the related CO2 emissions and the investments that are needed for new equipment additions.
In the last part of this building's energy demand modelling session, I would like to provide several examples of the results of our modelling, specifically the results of our modelling applied to the Africa context, and use these results to reinforce the importance of efficiency gains and understanding the impacts of improving efficiency and changing technologies on energy demand. So these are some of the results that we can then communicate to policymakers to reinforce certain messages and the importance of taking steps and putting in place policies to achieve energy objectives. So here we've taken an example from the International Energy Agency's World Energy Outlook Special Report on Africa, published in 2019. So looking at electricity demand from household appliances in the year 2040 under two different scenarios. Now, if we look at the left part of the figure, we can see that under a scenario where the current and announced policies are enacted and economic growth follows an expected trajectory as announced by the International Monetary Fund, then we can see electricity demand across Africa for these uses, for residential uses, increasing to around 350 or close to 400 terawatt hours. However, if we pass to a scenario where economic growth in Africa is much more rapid, so economic growth is in line with the expectations for African countries, and we also have energy access, so universal access to electricity and to clean cooking, which is achieved by 2030, so in line with the Sustainable Development Goals, then we see a much more rapid growth in energy service demand. So obviously, if we come back to the activity variable story and the bottom-up modelling process, then higher economic activity means higher average household incomes. This then translates to greater floor area on average per household, much higher household ownership of appliances such as refrigerators, televisions, washing machines, and higher household ownership of cooling equipment such as air conditioners. So if we just added to the system the same equipment that was being used in the STEP scenario, then we would have a huge increase in electricity demand. So going from around 350 terawatt hours to over 1,000 terawatt hours. So this obviously has very important implications for power systems and for the costs needed to increase generation capacity, increase transmission capacity, and then for energy bills, electricity bills for consumers. But what we want to show here is that by improving the efficiency of the appliances that are added, we can drastically reduce the impact of all these additional appliances. So that means that we can have a big increase in demand for energy services and so in quality of life because people have more appliances, but we've limited the impact on the energy system. So that's through greater efficiency. And so if we look at the right-hand side of the figure, we can see that the very important differences in the ownership variables for different types of appliances averaged across Africa. So we can see that we have significant growth already in the steps, especially in appliances such as televisions and refrigerators, but also in air conditioners, although they do remain at a much lower base. However, if we look at the Africa case, then this growth in ownership really does explode. So obviously this is important. It's people getting access to services, but via the modeling, we understand that as we put in place more efficient technologies, so thanks to policies, then we can limit the impact on energy systems of this increase in energy demand, energy service demand. So to be able to do this sort of analysis, we also need to have the modeling in place, but we need to understand what policies are in place today and what are the efficiencies of existing equipment and equipment being sold. For instance, we'll need to know how efficient are the air conditioners being sold today and what policies are in place that would impact the efficiency of these air conditioners. So that provides us with a baseline, and we can also look at how that policies and the policy change over the last years has impacted the energy intensity of these end users. So here is just an example where both heating and cooling policies have been tracked, and we can look at the building stock and the useful energy demand in terms of understanding which part of that energy demand is covered by policies or not covered by policies. And then based on that, we can understand how stringent is the average coverage across the building stock. And so what we want to see is that the stringency improvement really brings down the energy intensity of meeting demand for services such as cooling and heating. And if we take the example of water heating, then here we're looking at the evolution of energy demand in 3 different scenarios. So the first scenario, the RTS, is a scenario similar to STEP. So here we're just looking at the policies that are in place and the policies that have been announced, whereas the 2 scenarios to the right are more ambitious scenarios that meet climate objectives. So a 2-degree scenario and a below 2-degree scenario. So what we see here is just pure outputs of our model when we impose the constraints of saying we need to reduce emissions in line with a certain scenario, so 2 degrees or beyond 2 degrees. Then that means we need to see a big change in the fuel mix. And so this is obviously bottom up. It's coming from us saying we need to allocate a renewable technology as opposed to a fossil fuel fired technology. And these are the evolutions of the energy mix that then result. So it's these kind of results that can provide a visual communication of what the modeling is doing and then help us to bring together key messages and key numbers to communicate to the policymakers who can then act on the information coming from the model. And one final slide here is very specific to Africa and specific to cooling, to again underline the importance of increasing efficiency. So Africa's cooling needs, as many of us know, are much higher than most other places in the rest of the world. Many locations across Africa have cooling needs that are an order of magnitude higher than in countries such as France or Italy. And these cooling needs also dwarf major cooling demand centers of China and the United States today. And we see that almost 700 million Africans today live in areas where the average daily temperature exceeds 25 degrees. And average temperatures are often 1 to 2 degrees higher again in cities. And as Africa's population increasingly urbanizes, cooling needs will further grow. By 2040, the number of Africans living in hot areas approaches 1.2 billion people. As populations expand, especially in cities, and average temperatures increase with climate change. High cooling needs today and higher cooling needs tomorrow contrast with some of the lowest levels of air conditioner ownership in any region. Averaging today only 6 units, so 6 air conditioners on average per 100 households. Now, obviously, wealthier countries across the continent, such as Morocco, Algeria, and Tunisia, have higher ownership rates that can be up to 3 times the average of the African continent itself, while less affluent countries with often much higher cooling needs have ownership levels that are only half the African average or less. So as a consequence of this low average ownership of cooling needs, electricity demand for cooling today is very, very low in Africa. But the potential for future growth is strong. Ownership of cooling devices sees an important increase in our Africa case in response to these higher average incomes I described earlier and rates of access to electricity. So we reach in 2040 an average of 25 units per 100 households, but this is still well below the global average today. Ownership of fans increases further, but fans obviously have a lesser impact on electricity demand. So if we focus on electricity demand from air conditioners, then we can see that electricity demand in the residential sector across Africa for this end use could grow to well over 200 terawatt hours by 2040. So that is just a huge increase in demand that would have major implications for power systems, especially because of the fact that air conditioning electricity demand is often concentrated in certain hours of the day, so difficult to manage. But the importance here is to use the building energy demand modeling to understand that if we change the efficiency of these air conditioners, then we have the potential to cut this future growth in half. So we can reduce costs for the power system, reduce costs for the consumer, and reduce emissions. So here, this is again the messaging using the model to understand if we change certain variables, such as putting in place a policy which improves air conditioner efficiency, what are the results that we could expect?
Okay, perfect. So I hope everything was clear. So we will now, and I hope now you are able to see my screen. I think the last part presented by Tim. Sorry, maybe resume share. You should be able to see my screen. Write me in the chat if there is any issue in doing that. I think that, let's say, the last part presented by Tim is the perfect, my colleague Tim is the perfect introduction to our next step, which is actually doing, or at least having a look to today's exercise. So the focus today is on the cooling sector. And basically, so this is from the handbook, just to remind you. So you have this file on the Google Drive repository. You can then download it together with the Excel file that I will also later use. So you have in the table of content the chapter with the modeling exercises without the solutions, and then you can move to the solutions. So again, as usual, my suggestion is to start from this chapter to try to do the exercises without looking at the solutions, and also to take the clean version of the Excel file. If you encounter any issue, you want to have some hint, you can do it by going to the solutions part, and you will find the results. So today, since we don't have time and it's also a bit complicated to do it through Zoom, through the Zoom platform, we will just have a look to the exercise. I hope some of you were able to try to do it by themselves. Otherwise, feel free to do it today. And if you have specific questions, you can write me and we can have a look at your doubts and to see. But in any case, I suggest you first to look at this document, and also if you want to rewatch today's lecture, which will be uploaded on YouTube very soon, so that you have the possibility also to go back on specific part and having a look to them a second time. So I will directly move to the exercise 2 so that we can have a look at how it's structured and how we can solve it. So what's the approach in solving it? So the question for this exercise, so let's say the context, is that you have been asked to estimate the future demand for electricity meeting cooling needs in the building sector. So the Ministry of Energy of an hypothetical country wants to anticipate future electricity demand from buildings and to develop energy efficiency policies. So to do that, they need you, in this case, to do some analysis, some modeling, and anticipate what could be the future demand for electricity, specifically in cooling. So as for the last time, you will see the model if you didn't do it. But this is really a simplified version of what could be, let's say, a real life problem. So this is the structure of the Excel file I will be sharing in a few minutes. You have these drivers in the first column. So you have the GDP per capita, you have the population, you have the number of households, you have the AC units, you have the service demand intensity, and you have the electricity demand. So you have all of them have clearly specific units of measurement. So if you don't have clear in mind the concept of drivers and why these specific drivers have been chosen to be drivers to be taken into account during this exercise, I invite you to go back to today's slides and also to watch again today's lectures by my colleagues. So from, let's say, the clean version of the Excel file, you have this information here on a yearly basis, here just for the sake of being able, let's say, to have it on a PDF document. They are just on with 5 years time span, but on the Excel file, you have all years. So you have 2000, 2001, 2002 till 2018. So for all these drivers, you have all the historical data that, for example, come from specific agencies, specific ministries. So you may have the population information we also had in the previous lecture that, for example, comes from the ministry in this hypothetical country, which is in charge, for example, of demographic analysis. You have AC units, number of AC units, which again, the vast majority of the time come from surveys, from census processes, but maybe it can come also from actually the companies which are selling AC units in the country, which can report to the ministry the amount of AC units, for example, they sold in a specific year or on a cumulative basis. You can have a service demand intensity, which clearly is in terms of kilowatt hour per service for each appliance. So this is really context specific. So you would have to have information on which are the type of AC units which are sold in your specific, in this case, hypothetical countries, but in your case, in Rwanda. And then you have the electricity demand. So the total electricity demand coming, I remind you, just from the building sector, and with specific focus on cooling needs. The only information you have about the future is just about two drivers, and it's about the GDP per capita and the population. So these two information again come from agencies which has mandate about these two drivers, which can, for example, give you projections for GDP growth for your country. So in this case, we have both the GDP and the population, and we have clearly the GDP per capita, which comes from the combination of the growth in GDP and also the growth in population that you, as you can see, for example, for this hypothetical country, move from 108 million people in 2018 to 143 million in 2030. You have specific assumptions which you have to take into account, and that also explain why we talk about a simplified model. So, the simplification here. So we are only considering households, so not the entire building sector. We are just looking at the cooling needs for households, so residential and services. So there are several technologies providing cooling services. In this case, we will have, let's say, a restricted number of like portfolio of technologies for AC units. We have, but I will skip these assumptions because they are basically explained during the exercise. So you have specific questions which are again in the second chapters, in which you have the clean version of the exercise without the solutions. But starting from question 1, which is within the step 0. So the first thing, if you remember also from last time, we start from with analyzing the historical data, because before, let's say, diving into the future, it's important to have a look to the past trend. So the first question is, up to today, how have evolved some relevant indicators like GDP per capita, household occupancy, and number of AC units per household. So you have those information in the past. If you look at the Excel file, you will see that some cells are empty. And for each specific question in this document, you will see highlighted in yellow, and then highlighted in yellow the specific cells you are supposed to fill when answering each question. So I will really, it's really simple, also compared to the previous exercise we had, but really just have a look to how to calculate this information. And just let me again remind you to pay attention to the units of measurements, because sometimes, for example, in this case, when you are asked to do some specific calculations, the unit of measurement of each of these drivers is specified. So in order to have let's say, the same results also with respect to the Excel solution file. You have to pay attention when you do conversion between different values. So the second step is making projection on the relevant drivers. So as I said, in order to estimate future electricity demand for residential cooling needs, we need to first start from the past trends, and in this second step, like step one, we try to anticipate the future. So question 2 is how will households' income or GDP per capita evolve in the future? So you have different approaches you can take into account. One is, let's say, a linear regression that you can use in order to estimate, for example, the household, like both the AC unit, the AC units per household, and as a function of GDP per capita. So in this case, we use GDP per capita as a driver in order to derive what could be in the future the AC unit per household on average for the country. So first you have to assess what has been the function representing this growth, so this relationship between the AC units per household and the GDP per capita. And then once you have done it, you can try to do it for the future. So I will again skip it, but in this specific exercise, we want you to compare two approaches. So one linear approach, which is this one that you will see also in the solution. And in order to do that, you can use the trend line function from Excel. But sometimes there isn't like a simple linear relation between drivers. Sometimes you have to take into account different, but clearly also Tim during today's presentation explained it very well. And you can see, for example, in this case that we are not talking about a linear dependency relation between the two drivers in this case, which I remind you are the occupancy of the household and the GDP per capita. So you will have to use different function and a different curve. So our suggestion in this exercise is to try to use different trend lines, and using the R parameter, the R square parameter, which gives you, let's say, an assessment, like a feedback on how well the function you have chosen fits your data. You can choose which is the best trend line to use in order to first depict what has been the past, but in order then to use it to anticipate what will be the future, in this case, in terms of household occupancy, that will be then used in order to assess the energy demand. Let me check. Okay, I don't see any question in the Q&A and any raised hand. So please, if you have questions, really feel free to raise your hand or to write in the Q&A box whatever question you may have. So the fifth question is, how will the number of households in the country evolve in the future? So this is, again, really similar to what has been done for the previous question. Try to find which is the best way to, like, between a linear regression or different trend lines. Again, I'm referring to the Excel tool, the Excel functionality, in order to better represent the driver trend in the past years, and then in order to anticipate what could be the trend in the future. Same with respect to the number of AC units, which, the sixth question is, how will the number of AC units evolve in the country? Again, you will see from the Excel file. I will also open it right now so that you can see that you from in the sheet with the solution, you can see the functions used to calculate each of these drivers. But again, the approach is, let's say, really similar. You first look at how AC units were calculated. Like the AC units were like an input, but using the other drivers, you can derive their values. So when I will move to the Excel, you will see how using the same formula you can use in the historical period, you can do the same for the projections. Okay, let me jump to the Excel file. In the meantime, I think my colleague Victor joined us. So if you have question again, he will be here to help me answering the questions and doubts you may have. So here, this is again, as I was saying, the file for the this is just one file for all exercises. So you have to find the exercise model 2 questions and solution. And here you have question 7 from the handbook, which was asking you how will, sorry, I can show it here. Okay, so how will energy service demand per equipment evolve in the future? So this is really key to understand how much services is demanded by each cooling equipment, because based on that, you will have you will be able to anticipate what will be the energy service demand for all the equipments in a country. Sorry, Zoom is telling me, okay. Now you should be able to see my Excel file. Let me know if there are any issue. Is it okay? Just.
Yes, now we can see the Excel file.
Okay, because Zoom is okay. Perfect. So this is really crucial, and you can calculate how this variable evolved over the past and define a growth rate to apply in the future. So you take the historical compound annual growth rate between the previous years, and in this case, you will see that this value is equal to 4%. And you can use this value in order to anticipate the trend, like the growth in terms of energy service demand in the future. Then next question is question 8. What is the historical and future total energy service demand for residential cooling? So as I was anticipating you, when you move from one like you have to move from one specific equipment to all the equipments, so all the appliances in the country in order to model, because if you remember, this exercise came from the Ministry of Energy. So the deliverable you are supposed to deliver is referred to the entire country. So in this case, since you already calculated the trend in terms of total AC unit in the future in the entire country, you can calculate the total service demand by just multiplying the AC unit by the service demand intensity, clearly in the future. And again, I remind you, in this case, the exercise was asking you to deliver this value in terawatt hours. So you have to take into account this, and in the Excel file, you will see that we divide this value by 1,000. Just to be clear here, how you can use, for example, this 4% in terms of growth rate for the service demand intensity, you just have to multiply for each year in the projections period by 1 plus the percentage increase that you have calculated based on the historical trend. So the next question is in step 3, which is the estimation of the future energy demand. Okay, so the question 9 is calculate the historical efficiency levels. So okay, so this indicator can be calculated with the total final electricity demand and the total service demand. So in this case, for example, you have the efficiency here, which is simply the ratio between the total service demand and the electricity demand. So you have here the efficiency. In this case, both, as you can see, both terms have the same unit of measurement, so you don't have any conversion factor to take into account. So in this case, you can, let's say, project the average efficiency. In this case, it's growing over the year, and you can also see it from this chart. So the next question is starts complicating a bit the exercise. So the question 10 you will find tells you that there are various technologies used by households for cooling. So I said this is really a simplified exercise because maybe we could have more than 3 technologies in a country for cooling, but in this case we use just 3. All of them clearly have different, you have different information. So for example, in this case, you have that all of them have different efficiencies, but the exercise is actually asking you to calculate both these efficiencies and in the second step, the market share. So here you have that the calculation for the market share is, because now not being able to share both the Excel file and also the PDF is a bit difficult for me to show you, but you have specific information to take into account. So for example, if you look at the exercise, you will see that the historical data reflect different performances of our 3 technologies. So we have, let's call them basic, intermediate, and super advanced AC units based, for example, on their efficiencies. And you will see that the exercise is asking you to take into account different trends in terms of efficiency growth, because you will see that the basic version, for example, is increasing with a 1.5% efficiency rate per year. So you will see how this value will be, for example, in 2030. But we have the super advanced AC unit, which starts from an higher value and also grow with an higher growth rate, and is reaching very high values in terms of efficiency in 2030. So one of the questions you will encounter, which is question 11, question 10, is asking you, as I said, to calculate the market shares based on specific information you will find in the text. So for example, the text tells you, and clearly those assumptions doesn't, let's say, fall from the sky. You may have them when doing such an exercise in real life, interacting with the relevant stakeholders, the key stakeholders in the domain. So in this case, they could come from different ministries, from different agencies, or directly working, interacting with the private sector, which is selling, for example, these technologies in your target market. So the exercise tells you, for example, that technology 2, so it starts from technology 2, saying that it will continue its historical expansion and that its market share will increase at a rate of 1% per year. So in this case, you can see that the market share of technology 2 is increasing by 1% each year. So you know also that the super advanced technology, so technology 3, will start just in 2019. So let's say in the next year, you know that there is this new company which is entering the market and will start to sell this technology with we start to sell this technology, and this means that till 2018 the market share, for example, of technology 1 will be just 100% minus the value of the market share of the technology 2. But another information you have from the text is that in 2030 technology 3 will be reaching 7.5% in terms of market share. So at this point, you can again calculate the market share of technology 1 as 100% minus these two, and you can calculate the market share of technology 1 like going backward, starting from 7.5, which is the value you were told by the text that it will reach in 2030, because you are also told that this technology will grow with the, like in terms of market share, with the linear approach, so with a linear trend. Okay, so the 11th question, again in this step in which you are required to look at the future, is what will be the average efficiency levels of the entire portfolio of technologies in the future? So you have oh, sorry, I think. Okay, just 1 second. Let me check if, okay, I don't see any question in the Q&A box or in the chat or any raised hand. So if you have question, again, feel free to raise your hand or to write so that we can answer you. So the next question is to calculate the average efficiency levels of the entire portfolio of technologies in the future. So starting from the previous answers in which you calculated the market share of all the 3 technologies, you are asked to do basically a weighted average calculation in order to calculate these efficiencies. So again, I invite you to have a look to the Excel file in order to see how you can answer this question, also because we are a bit late in time. So I will finish with the last question, which is actually not a question, but it's like a suggestion, an indication that you can, by plotting all this information you have calculated, you can do what we have called a sensitivity analysis. If you remember, I also introduced that in the previous lecture, because now that you have this model, because this is basically, even though if it's a simplified model, you have a model which represents, in this case, for example, the trend. In this case, we plot these 3 charts. You have the service demand intensity, you have the overall efficiency, and you have the total electricity demand trends from clearly this, which is a straight line, like not a dotted line, full line, is just historical information, historical data. But the dotted one, the dotted space represent clearly the future. So by changing some of these parameters, you are able to do what's called a sensitivity analysis, and also to understand what are the parameters and the drivers which are which will play a major role, for example, in defining the trend for example, the service demand intensity and the overall efficiency in the next decades, and be able to answer, for example, a decision maker like the Ministry of Energy in this case, which asks you to do this modeling exercise. So I will stop here since we are it's 5 p.m. So if you have questions, as I said, my colleague Victor reached us. You can write in the Q&A box. You can raise your hand, and he will help me if you have questions in answering them. Hi, Victor, and pleased to see you.
Hello. Can you hear me properly?
Yeah, perfectly.
Wonderful. Yeah. Thank you very much, Erlen. Really looking forward to any question you might have on the methodology.
Yeah, I see there is a question from actually an anonymous attendee. So if you want, we can see it.
That's a really nice question indeed. It's a bit broad. I don't know if you are thinking about a specific energy sector or more as the whole energy sector, let's say. But since this is based on buildings, I would assume you are asking about buildings, and that's the data you require and indicators you want to develop. Really, to collect the data is very costly. As you all know, it's very difficult to find the data, but of course, it's one of the best things you can do because the model is going to be as good as your data is. So if you put garbage in the model, you're going to get garbage out. This is one of the most famous sentences from the modeler. So the first question you have to ask is, what do I want to answer with this model? So for example, if I want to see if in my country the space cooling energy consumption, it's a problem, how can I improve that? Then I would decide to collect, okay, I want to collect air conditioning units. I want to collect all the imported energy conditioning units that are coming to the country. How efficient those units are being, how efficient are the units that are being sold in that market? What are the shares of the market as we were seeing in the exercise? So really, we have to start thinking from what do we want to answer, what data do we need to answer those questions, and then we can model, we can do all those projections to try to answer those questions, to try to design those policies that then will be beneficial for the people that will help us achieve our goals. If we just collect data without a purpose, let's say, then that's not the right approach. It will be more costly and with less benefit. Of course, if you want me to cover a specific energy sector, or if you are more curious about it, but on general terms, on your question, usually you need a lot of energy consumption data. The more the detail, the better, like the energy you consume for space cooling, space heating, appliances, also the quantity of units, the ownership, the people that live per household. All those data are usually very useful, but again, we will have to select the ones that will help us answer the questions we want.
Perfect. Thank you very much, Victor. I agree that the question was a bit broad, so I saw that the person which asked it also put it in the chat. So I hope Ismail. No, sorry, it was Jovin. That the answer is aligned with what you were expecting. If you want us to maybe give you more data and indicators in terms of list for a specific sector, feel free to write me an email or so to Victor or to me, and then I can forward it to him, and we will try to give you some information and maybe share some links from our website in which you can see how, for example, we do this kind of modeling here at the IEA.
Indeed, in fact, I'll try to share right now a manual that the IEA developed, which I think it's something that we cover here in this training as well. That it's called the Manual for Energy and Efficiency Indicators, and in that manual it covers all the data you can collect for the different sectors, not only residential, but services, industry, transport, and also which kind of indicators you can develop, and also what would be the details. So I'll try to find this link and share it with you.
Perfect.
So you have,
thank you very much.
Which I think will cover exactly the list you probably are looking for.
Perfect. Thank you very much. I see there is another question from Ismail Mohamed. So what is the best method or energy database management system?
Well, that's really depends on again, what are the needs of your organization. I have to admit that this is a little bit out of the scope of the building sector questions. So this again, it's really depending on what you need. In the IEA, for example, we have a centralized database that we use to share data, to feed the models, to also store the output models. It's based in SQL, also in Python. We use a lot of Excel. But again, this would really depend on what's the purpose of this database.
Yeah, I definitely agree. It's really, there is no like good for all, let's say, solution in any case when we try to address this topic. So again, Mohamed, if you want specific information with specific case application, feel free to write an email and we will see what we can do. Okay, thank you, Victor, for sharing the link. So for all the attendees, you can see in the chat. Because you put it, I'm the only one able to see it actually. Okay, no worries. Okay, so now you can see the link to the energy efficiency indicators manual on statistics developed by the IEA. And maybe, probably you will see the list of indicators Jovin was asking for. But if you think that that list isn't exhaustive, if you want specific clarification on some of the items in the list, feel free to write us and we will try to be as much as we can exhaustive. Okay, perfect. I don't see any other question. We are also a bit late, sorry for that. But it's better to answer your questions since we are here for that. Thank you very much, Victor. So I remind to our attendees that tomorrow we will have the third lecture on modeling. So see you tomorrow at 3 p.m. as it was for today. Have a nice day, evening, and see you tomorrow. Bye. Thank you, Victor, again.
Thank you. Bye.